Hello everyone. So, before we begin, first thing, today's lecture video will cover material that will not appear on our exam 2 this coming Wednesday. So because of that, I actually encourage you to come back and watch this video after the exam. But with that out of the way, today's lecture video is going to cover a topic known as inverse functions, and conversely we'll talk about the graphs of inverse functions. So, let's get right on into it. Okay, so before we start talking about inverse functions, let's go ahead and recall what we know about functions. And what I mean by that is just, what is the most general way we could possibly describe a function? Well, one such way we could do that is that functions, in the most simplified terms possible, these are things that take inputs and create outputs, right? At the bare bones, this is what a function does. You plug something in, the function outputs something else. So, how we like to denote that visually is, given two sets of numbers, one we'll call our inputs, and one we'll call our outputs, right? We can have a function, say, f of x equals x plus 3, that takes all the numbers in the set of inputs and maps it to a corresponding set of outputs. So, for example, if we had the input 4, right, this would be mapped by the function f of x to the output 7, because 4 plus 3 is 7. Right? That's how they work in general. So, what today's topic of discussion is going to be, well, considering some certain function that maps an input to an output, all we're going to be talking about today is this. Well, understanding that's how f of x operates, let us then think of this function in addition to f of x. Let us consider the function that takes 7 and maps it to 4. And we'll call that g of x, right? And what we can see is special or significant about this g of x function is that while f of x took this input 4 and generated this output 7, g of x is undoing that. G of x is taking the output and bringing it back to the input we started with. G of x is undoing f of x. Okay, and that's going to be the general idea, the big picture idea for today's lecture, is that when we're talking about inverse functions at their core are given some function to be an inverse function of that function. So for g of x to be the inverse function of f of x, what that means is that g of x undoes f of x. That's the big idea for today, right? And we can actually understand what g of x is, what it actually is, right? So f of x was the function that took an input and added 3 to it. In order to undo that, if I want to undo an addition of 3, I need to subtract 3. So g of x equals x minus 3. So this was kind of just the big picture introduction to inverse functions. Hopefully this visual helps. And yet again, just to emphasize, the big picture idea is functions take an input, make an output. Corresponding inverse functions undo that. They take the output and they bring it back to the input. Alright? So let's go ahead and try doing some more concrete examples of this. Start. Okay, so for our first example, we are going to consider this following question. We're going to informally find the inverse. In other words, we're going to consider this question. What g of x will undo f of x? And for us, our f of x is x divided by 6. Okay? So before we begin, I do want to emphasize that this example is a informal process to finding the inverse function. It's going to be much more just like us talking it through and logical understanding of how we generate the inverse. But later in this video, we are going to give a much more procedural method for finding an inverse. And that method that we're going to talk about later is what I would expect you to do in homeworks and exams. This is us still just trying to lead into that. But for now, let's start with this example. Alright, so we have f of x equals x divided by 6. So let's write that in words, right? We're still doing this informally, so let's in words describe what this function is doing. So f of x divides x by 6. Okay? So if we understand that the general core of today's concept is that inverse functions undo another function. So my g of x that I'm going to make, I want to undo this division by 6. Alright, so what we can think of when trying to generate these inverse functions is just whatever that function does, however you just describe it in words, go in the opposite direction of how you describe it in words and undo everything you see. So in other words, I see a division by 6. So let me say then my inverse function, g of x, has to undo a division by 6. Well, if you just think about it, if I'm dividing by 6, what's the opposite operation when we think of division? Multiplication. If I'm dividing by 6, I want to multiply by 6. Alright? So to undo that, we need to multiply by 6. Alright? So if I want to undo a division by 6, I want to multiply by 6. Therefore, my g of x must be 6x. And there you go. That's my inverse function. Okay? Hopefully, maybe, you're not blindly trusting me and you're asking the question along the lines of, well, how can we know for certain? How can I know for certain that is my inverse function? Where's the proof? That's a great question to ask, and we'll explore that in our next example because it'll be a much more interesting one to work with. So let's go ahead and get right into that actually. Okay, so let's do this next example. Same premise, let's talk about informally finding the inverse, and the function we'll consider now is 2x plus 5. Okay? So then, yet again, just because we're doing this informally, let's take the time to describe what this function is doing in words. Okay? So f of x multiplies x by 2, then adds 5. Alright? Now, what I want to take note of here is, notice how I don't write f of x adds 5 to x, then multiplies by 2. Right? Those are the same operations that we described here, an addition by 5 and a multiplication by 2, but they're done in a different order. And we have to remember that order in which we describe operations is extremely important, right? Going back to PEMDAS all those years ago, there is an order to operations that we have to follow, parentheses, multiplication, all that type of stuff, right? So when it comes to describing the orders of this operation, multiplication goes first before addition. So that's the way we describe this in words. Now, why that's important is because, as I mentioned in the previous example, when it comes to trying to understand what function we need to make, what g of x will undo this f of x, right? Start at the end of your description of f of x. Start at the end there and work your way backwards. From the end, undo everything that's been piled on. So if I start from the end, the first thing I see is addition by 5. So when I'm describing g of x, that's what I have to start with. I start with that addition of 5, so the first thing I'm going to say that g of x does is that g of x has to subtract 5. So g of x must subtract 5. Again, I'm starting with that subtraction of 5 because I want to start at the end of my description for f of x, and I want to move backwards. I want to undo everything that's been piled on. Alright? So, I subtract 5. That's from I got this adding 5. Then I move along here into the next operation. Oh, I forgot the 2. Multiplies x by 2. So then after I look at this addition by 5, that's when I see this multiplication by 2 in the description of f of x. So going back to g of x, that then must mean, so subtract 5 from x. Then if I want to undo a division, or if I want to undo a multiplication by 2, that means I need to divide by 2, then divides by 2. Okay. So then again, when it comes to writing what g of x is from this description, have to keep in mind the order in which we describe things. First thing that is described is the subtraction by 5. So we start with x minus 5. After this subtraction by 5, only then do we divide by 2. So that means I have x minus 5 divided by 2. Okay? An important thing to note is that I did not write x divided by 2 minus 5. Right? So, again, if we were to describe this function in words, I would say that function takes x, divides it by 2, and then only after the division do we subtract by 5. That does not agree with the description we just wrote up here. This description is saying g of x must subtract 5 from x, and then only after you've done the subtraction does division take place. That is why we have to write the function this way. That is why we do not write it this way. Okay? So this whole thing just comes out to be an example to help emphasize again this idea of the order of operations and why orders are important, because that's kind of an underlying idea behind these inverse functions, is that since the core of it is to undo a function, you need to be very specific in the order in which you undo the operations. Alright? So a very subtle point, but a very important point for today's lecture. Now, going back to that question I proposed earlier, though, is how do we verify? Like, how do I know for certain? How can I be confident that this g of x I just described is my correct inverse function? Well, to gain that confidence, we're going to have to consider the following idea. So, in order to get that idea, I'm going to need to erase the board. If you haven't done so already, go ahead and pause the video to copy now. Okay, so to build that confidence of understanding that the g of x we created here actually is the inverse to this f of x, we need to consider the following question then. And this is going to lead us to a pretty big idea for today's lecture. And the idea is this. What would happen if I took the composition of f and g? Alright? And hopefully we all recall what composition means, and we understand that this is the formal way of writing composition, but we all hate that way of writing it because it makes no sense intuitively, and that this can simply be translated into the much more intuitive way of writing it of f of g of x. That is what compositions are, plugging one function into another one. So let us consider this question using these two functions, one we were given and one we made. All right. And what I encourage you at this point is go ahead and pause the video and work through it on your own and see what actually happens when you take the composition using these two functions. So go ahead and pause the video now and work on that. Okay, so hopefully what you were able to see is that f of g of x, the composition of f and g equals x. Alright? And that right there, the fact that the composition of these two functions equals x, is what we're going to come to know as being the definitive proof, the evidence we are looking for to be confident that this g of x is indeed the inverse of f of x. This is exactly what we're looking for. Okay? And let's spend some time thinking about that. Because it's a pretty interesting idea to think about, is why is this statement the proof we need? This is the proof we need. Proof that g of x is the inverse of f of x. Alright, that's the proof. Well, if you try to think about it on a more conceptual level, and we remember that the core of today's lecture is this idea. Inverses are functions that undo another function. Okay? So, whatever f of x does, it multiplies by 2 and it adds 5. G of x wants to undo that. Hence, it subtracts by 5 and divides by 2. Okay? So it is any surprise that when I take the composition of these functions, in other words, when I take one of these functions and I plug it in entirely, I plug the whole thing into the other function. However, what's important to note is that I constructed my g of x in order to undo my f of x. So if I'm taking that g of x and I'm plugging it into my f of x, right, f of x is going to have its own set of operations, but g of x is going to have an entirely different set that directly undoes whatever f of x does. So if I'm taking their composition, I'm plugging one function into another one, when they combine, all these different things they do, they're going to be canceling each other out, right? Because that's exactly what our goal was. That's exactly what we intended to make. So if you take their composition, all these crazy operations you may have, they go away because they're being canceled out by each other. And then if I'm going to have some value and I'm going to plug it in, well, are there going to be any operations left to use after I've taken the composition? And if you think about it for a bit, you realize that no, there shouldn't be any left, right? If I've done my job successfully, every operation should be canceled out by a different one. And so whatever I plug in should be exactly what I get outputted. A more visual understanding of this is going back to that picture we drew. If I have my set of inputs and I'm going to have some f of x that maps it to a set of outputs, okay, well, what does g of x do? Remember, we said that g of x took the output and brought it back to the inputs. So just continue the chain. Right, just continue the chain. If we have an output A, if we have an input A, f of x will take that input A and say map it to B. But then what g of x is going to do, and what we described in that picture earlier, is it's going to take that B and it's going to bring it back to A. Right? It's undoing whatever f did. And so this is the big idea, is that when I compose my functions, there should be nothing happening anymore. Everything goes away. Everything is canceled out. And so whatever I plug in into the composition is exactly what I should be outputting. And this idea right here, this idea of the compositions canceling each other out, becomes the core of the formal definition of an inverse function. So let's go ahead and see what that formal definition is now. Okay, so here's our formal definition for inverse functions. Right? So it goes like this. Let f and g be two functions such that f composed with g of x equals x for all x in the domain of g, and g composed with f of x equals x for all x in the domain of f. Alright? So in other words, regardless of the order of the composition, the fact stands that the composition of these two functions equals x. That's the big idea. Now if this is true, then we get to call g of x the inverse function of f of x. So this is the requirement and the definition of what it means to be an inverse function. Two functions are inverses of each other if the composition of these two functions equals x. Alright? Now what's important to pull from this definition is that if we get to call f of x, or if we get to call g of x the inverse of f of x, then we denote g of x like this. F to the negative 1 of x. We read that as f inverse of x. That is our notation for inverse functions. Okay? So, just using that new notation, we then get that the composition of f and its inverse equals x, or conversely, the composition of the inverse in f also must equal x. And this is it. This is going to be our formal definition for inverse functions. Again, the core of it is that idea that when you compose these two functions, they cancel each other out, and all the output is x. Alright? Now, there are some very important notes we need to make about this definition. So let's go ahead and talk about those next. Okay, so there's going to be three very important notes we need to make about inverse functions. The first one is this. It's this idea, it's just a building upon the relationship between f and inverse, f inverse. The relationship being this. The domain of f, is the range of f inverse, and that's the range of f is the domain of f inverse. Alright? So, in other words, if I have the domain of f, or in other words, the set of outputs for f, so the domain of f, which again is just the set of inputs of f, is exactly the set of outputs of f inverse, or in other words, the range of f inverse. And conversely, the other way holds as well. So that's our first very important note. The second important note about inverse functions is this it's an important thing to note is the question, what is the inverse The second important note is this question. What is the inverse? What is the inverse of f inverse, right? If I have the inverse function, what is that function? Inverse function's inverse? A bunch of tongue twisters. I actually encourage you to think about this for a couple seconds. What is the inverse of f inverse? All right, so hopefully you're able to see, and if not, no big deal. We'll talk about it now. The inverse of f inverse is f. All right, and that's not too surprising because going back to the definition, what does it mean to be the inverse of another function? It just means that when you compose the two functions, the composition of those two functions produces x, right? So if I have an inverse function, then the only function that exists which, when composed with that inverse function, produces the output of x is the original function we built that inverse around, right? Very subtle point, very important point. So that's why I bring it up. And then lastly, the third most important point is directly a result of the fact that we mathematicians are incredibly lazy and we like to reuse notation, and it causes a lot of confusion for other people. And the point I'm trying to get at is we have seen and we have used before the fact that x to the negative 1 power equals 1 over x. That is what we gave the definition, the meaning behind negative exponents. It's you just make it into a reciprocal. Now, what we have to understand, and I'm going to emphasize right now, is that f inverse of x does not necessarily equal 1 over f of x. Okay? We've seen it already in our previous examples. Go back to our previous examples. The inverse functions were not simply 1 over f of x. No. So, do not get confused with this notation. I know we've used it before, and I know when we used it before with negative exponents, we took that to mean 1 over x, right? That is not what it means here. This negative 1 we have right here, this is not an exponent. It does not operate in the same manner as an exponent. This is just the notation we use to define inverses. It's important to note when we're reading this that we understand the meaning or the context of the situation. It's all about context when you're reading mathematical notation. Here, this is a variable with a power. So that's why we know it operates like this. Over here, this is a function with that negative 1 power. So the context that this is being applied to a function, remember, it's all about context. The context here is that this is an inverse notation. It is not a power notation. Okay? Actually, I'm not even going to mention that. Just remember, this does not mean 1 over f of x. A very important note, because it's a very common mistake, and it is a horribly, horribly incorrect mistake to make. So, f inverse of x does not mean reciprocal. Again, this is a very common mistake to make, but a very wrong mistake, so let's try to burn it out of our memory, burn it out of our heads right now. Try our best never to do that. And remember, it's all about context. Just understand the context of the situation, what you're reading. If you're looking at a function, that negative 1 is not a power. It's denoting the inverse. Okay? So, well, these are the important points I wanted to make. And so let's now, because we've already done some examples about how to informally find an inverse, let's now get into what I've already talked about, or mentioned at least, is let's talk about this more formal or procedural way of finding inverses, because there is a common technique to use. So let's talk about that next. Okay, so let's go ahead and talk about the steps we have towards finding an inverse function. And what we'll see is it comes out to be a 5-step process. So step number 1 is whatever your function may be called. And what I mean by that is whether it's called f of x, h of x, g of x, whatever. Step number 1 is to replace that with y. So replace f of x with y. Okay, and this is kind of just a convenience step because as we'll see when we're working through examples, and in steps 2 and 3, it's just going to be easier to work with y's rather than writing a bunch of f of x's or things similar to that. So then step 2 is kind of where the magic happens. Step 2, this is kind of the core of the whole process. Step 2 is to take all your x's and make those x's into y's, and take all your y's and make them into x's. In other words, we want to swap all x's and y's. Okay? Key emphasis on that word all, right? Every x I see must become a y. Every y I see must become an x. All right? And like I said, this is the core of the process. This step right here, whoever came up with this step, kudos to them. Like, it seems like such a trivial thing to do, such a minor thing to do, but man, oh man, is it just a awesome, like just such a cool process, and whoever came up with it, wow, like this is just a smart thing to think of, because it does exactly what we're going to need to do. And step 3, right? So step 3 of this process is going to be, after you've done your swap, go ahead and solve for y. All right, and again, just to reiterate, what does it mean to solve for a variable? Well, to solve for y means you want to isolate y. You want to get that y by itself, have everything else on the other side of the equal sign. Okay, and what we'll see as we work through examples is that in that process of solving for y, after you swapped all your variables, resolving for y ends up making you undo all the operations and in the exact order you want to have them undone. Yeah, so in other words, this step from 2 to 3, or this jump from between 2 and 3, this is where that undoing happens, that core idea of inverse functions. This is where you undo operations. Okay, so then moving on from there though, step 4. Step 4 is to then, we started this whole process by replacing f of x with y. So at this point, at the end of step 3, we should successfully, if we've done our work right, we should have our inverse function, right? So let's go back and make sure we use the inverse notation is all step 4 is. In other words, replace y with f inverse of x, right? Make sure we're keeping in tune with that formal notation. Now, so at this point we have the inverse function, right? But I said this was a 5-step process. So what is this 5th step? Well, the 5th step is the most important step, and it's the universal step of every single process we ever learn in this class. All of these processes have the same exact last step, and as I said, it is the most important step, but surprisingly and not surprisingly, it is the step that everyone either forgets to do or doesn't feel like doing. And step number 5 is, of course, and forever will be, we need to check our work. Right? The definition tells you the composition of these two functions should be x, so go ahead and take the composition and see if it actually does equal x. But this right here, this 5-step process, is our manner, our method in which we will be using to find inverse functions. So go ahead and take a moment now to pause the video and get this copied down, and then let's go ahead and do an example using this. Okay, so let's go ahead and find the inverse function for 4x plus 5 divided by 3. Let's find the inverse. So, just walking through our steps, step number 1 tells us, let's replace that f of x with y. So we now have y equals 4x plus 5 divided by 3. Okay? Step number 2, we want to replace all our x's and y's, right? So this y must become an x, and this x must become a y. So I get x equals 4y plus 5 divided by 3. Now then, for step 3, and step 3 is kind of a umbrella step because there's going to be a bunch of steps we have to do through step 3. In other words, we want to now resolve this for y. So let's isolate that y. So first and foremost, let's multiply that 3 over. So we're going to get 3x equals 4y plus 5. Then we can subtract the 5 over. We get 3x minus 5 equals 4y. And lastly, divide by 4. So we get 3x minus 5 divided by 4. Okay? So we've now solved for y. So we finish up step 3. Moving into step 4. Step 4 tells us we want to replace this with the proper notation. In other words, write the inverse notation for a function. Beautiful. And last but not least, we have a proposed answer. Let's now confirm this is the correct answer by taking the composition. So I'm going to need some room to do that. So if you haven't done so already, go ahead and pause the video at this point to get this copied down. Then I'm going to go and erase the board and check the composition. Okay, so let's check our composition. So we have f inverse of x as being proposed to be 3x minus 5 divided by 4. So let's now take our composition. And remember, as noted in the definition, it doesn't matter which composition we take, as they should end up being the same answer regardless. So we'll do f composed with f inverse of x. So this means 4 times f inverse of x. And I've already seen I'm going to need more room, so let me go ahead and give myself that. I've lost my eraser. Oh, here it is. Going to need more room, so let me make sure I have plenty of room. I have f of f inverse of x. So we're going to have 4 times f inverse of x plus 5 divided by 3. So we're going to get 4 times 3x minus 5 divided by 4 plus 5 divided by 3. Okay, so our 4's will cancel. Alright, so I'm going to get 3x minus 5 plus 5 divided by 3. From here we can see the 5's will cancel. I'm going to then have 3x over 3. The 3's cancel, and I'm left with x, which is exactly what I wanted. There we go. We have our proof. We now have the evidence to support the fact that we have found the correct inverse function. And there it is, right? So there's how you walk through the process. The process itself isn't hard, but when you get to the nitty-gritty of it, especially that step 3, it can kind of get difficult depending on how many variables you need to juggle. But overall, in general, the idea behind how you find the inverse function isn't too difficult a process to wrap our heads around. Again, the difficulty probably ends up coming from when we're getting our hands dirty, depending on the function we're working with. So, there's our first example. Let's go ahead and try doing another example. Okay, so for our next example, let's consider the following function. F of x equals 3 over x plus 1. Okay, so we want to find the inverse for this. Now, this one is going to be for you guys. So what I encourage you to do now is go ahead and pause the video, work through this problem, see if you can find the inverse. And after you unpause, I'm going to go ahead and write my answer on the board without any work, and we'll go ahead and compare. Okay, so go ahead and pause the video now. Alright, so hopefully you gave the problem a shot, and you have an answer. So the answer I got was that f inverse of x has to equal 3 over x minus 1. Okay? So that was the inverse I got, and hopefully you got the same thing. If not, right, don't automatically assume I'm wrong. Or don't automatically assume that you're wrong and I'm right. It could be the other way. It's happened before. So double check your work and see if you still agree with me or you disagree. Remember, we do have the nice check we can do. Take your composition. If you take your composition, you can know for a fact whether your answer is correct or if it's wrong. So please go ahead and do that. And if you have any questions, make sure you email me. But with that out of the way, let's go ahead and move on to our next example. Okay, so for our next example, let's again just find the inverse, but let's go ahead and do a bit of a more difficult problem, but not really, as we'll see. That meaning, what I mean by that, let's go ahead and do a problem or a function that has exponents involved, right? So let's find the inverse of f of x equals the cube root of the quantity 1/3 x plus 2. So we have this cube root we now need to handle, but as we work through this problem, we'll see it's not a big deal. Still stick to our steps, do as they tell us to do, and the answer will come to us just as easily as the other example. So for our step 1, we're going to replace with y. Okay, step 2, swap our variables. All right, and then for step 3, now we want to solve for this variable y. Okay, so this is where we may get tripped up for a second because we have this cube root in our way, but it's nothing to freak out about. We just take a deep breath and we remember, well, what do I know about the cube root? Well, what I can remember is that cube roots can be rewritten as a 1/3 power, right? All roots are fractional powers, so let's write it as such. Now, if I'm looking at this 1/3 power, we just got to think to ourselves, right? How can I get rid of a 1/3 power? So we think to a moment, and hopefully eventually comes to us, and we remember that if I want to get rid of a 1/3 power, I need to cube both sides. And actually, let me draw that in a different color. So if I cube both sides, that'll allow me to get rid of the 1/3 on this side. And just to recall, why is that the case? Well, using our properties of exponents, I have an exponent taken to another exponent. What does that mean I do to them? I multiply the exponents together. I multiply 1/3 and 3. That simplifies down into 1. The exponents go away, right? So then I'm then left with x cubed equals 1/3 y plus 2. And then from here, it's a pretty straightforward linear problem to solve. Subtract 2 to both sides. I get 1/3 y equals x cubed minus 2. Multiply by 3, and I get y equals 3x cubed minus 6. There you go. So step number 4. Write this formally with the proper notation. So I get f inverse of x equals 3x cubed minus 6. And of course, what we'll do now is we'll do that step 5. We'll check our work. It's always like, I know even I've skipped over, I've definitely, I've skipped over plenty of check steps throughout this class. But for inverse functions, it really is an important step to check that your work is correct for inverse functions, because the check behind inverse functions is actually just the definition of inverse functions. So if you're not even satisfying the definition, then you better make sure you're clear on that so you can go back and find the error in your work. But I'm going to need to erase some of my work here to do the check. I'm going to erase this side of the board. So you haven't done so already, make sure you at least copy this side of the board down before I do that. So go and pause the video now to get that copied. Okay, so let's go ahead and do our check. So for step 5, I'm going to take the composition. So what I get is cubed roots of 1/3 times f inverse of x plus 2. All right. So then plugging in my inverse function, I get the cube root of 1/3 times 3x cubed minus 6 plus 2. Multiplying the 1/3, I get the cubed root of x cubed minus 2 plus 2, which is just the cubed root of x cubed, which is just x. So yet again, my check holds. I have the evidence to now claim that this is indeed the inverse function for f of x. there it is, right? So here's an example with exponents involved. And as we can see, it's nothing to freak out about. Just walk it through. Remember these properties of exponents, how to cancel fractional exponents, or just how to cancel exponents in general, because we always should be remembering that in this class at the very least. And there you go. This is this example. So with that out of the way, let's go ahead and move on to our next example. Do another one like this. Okay, so let's go ahead and consider this next example. Again, we'll find the inverse of f of x equals square root of x minus 5 divided by 2. And again, this one's going to be one where you guys get your hands dirty. So go ahead, pause the video at this point, work through this problem, see if you can get an answer, and then after you unpause, I'm simply going to write the answer I got, and we'll go ahead and compare. So pause the video now. Okay, so hopefully you gave the problem a shot, and let's now compare answers. The answer I got was f inverse of x equals 2x plus 5 quantity squared. This was the inverse I got. So hopefully we got the same answer. If not, double check your work. Check that composition. See if your composition work is correct. And if we feel confident you're right, go ahead and send me an email and we can go and talk about it. Maybe I made a mistake. Who knows? All right then. So with that out of the way, let's go ahead and move on from our examples of finding inverses, and let's get into a discussion of the graphs of inverse functions. Okay, so now let's go ahead and get into a discussion about the graphs of inverse functions. And before we start the discussion, I want to recall an important relationship between a function and its inverse function. That being, if I have the outputs of a function f, right? If I have the outputs of that function, then these must be the inputs for the inverse function. And also, if I have the inputs of my function, these inputs of my original function must be the outputs of my inverse function. Okay? So with that idea in mind, we can kind of build an understanding of what we expect the graphs of inverse functions to look like. What I mean by that is, if a comma b is a point on the graph of f, all right, if I have a point a comma b, and this is a graph, or this is a point on the graph of f, then I can make the claim about a certain point being on the being a point, or is a point on the graph of f, f inverse. Okay, so go ahead and think about this for a second. Think to yourself, what is this point? Right? With the understanding that a comma b is a point in the graph of f, and understanding this idea behind the relationships between functions and their inverses, we can make a statement about the graph of f inverse, and that it must have a certain point. So I encourage you to pause the video now and to think about this. What is the point that f inverse must have? Okay, so, right, going back to it, we have this point a comma b. It's a point on the graph of f, right? And we remember that for all points, the x value is our input and the y value is our output. Okay, well, so if I input a into f, that means I'll output b. All right, and then going back to our relationships revolved between f and its inverse, the outputs of f must be the inputs of f inverse. So if b is an output of f, then b must be an input of f inverse, right? Conversely, what will be the output here? Well, what was the input that generated b for f? The input was a, so that means when I input b into f inverse, I should expect to output a. Okay, and this is exactly the relationship that's going to build the graphs of these inverse functions. It's this idea that if you have the point AB on f, then you must have the point B comma A on f inverse. And what that ends up leading you to discover is that if you go ahead and plot a bunch of points, you'll see this relationship. I'm going to need to erase the board now, though, so if you haven't done so already, pause the video to get this all copied down. Okay, so this idea of AB being on f means BA is on f inverse leads you to this conclusion eventually. So it leads you to the conclusion that the graph of f inverse of x is a reflection of the graph of f of x, on the line y equals x. Okay, so this is the important note about the graphs of inverse functions. All the graphs of inverse functions are just a reflection of the original graph f of x over the line y equals x. All right, to help give a visual image to what we're trying to say right here. All right, so if we take the line y equals x, all right, here's our line y equals x, and say I have my original function f of x. Say I have my original function f of x, then the graph of f inverse of x is taking this image and folding it over the line of the line y equals x. In other words, it'll look something like this. And this blue line is f inverse of x. This is the big idea for graphing inverses. You just are creating a reflection across the line y equals x. Okay? So that's really all it is when it comes to the graphs of inverses. It's a pretty interesting thing to note is that they're just reflections. So now let's actually just go ahead and let's do a quick example involving graphing a function and its inverse. All right? So let's go and do that now. Okay, so let's go ahead and consider this quick example. Let's graph f and let's graph f inverse on the same coordinate plane. So we're going to have f of x equals 2x minus 2. So this will then mean that f inverse of x has to equal 1/2 x plus 2. Plus 1. Alright, so since these are both linear equations, right? In other words, their graphs will be lines. So in order to create a sketch of these lines, at minimum we need 2 points each. So we'll take the following 2 points. We're going to get the point 0, 2 and 2, 2 for f, and the point 0, 1 and 2, 2 for f inverse. So then, creating our sketches, right? Again, since we are graphing both the function and its inverse, we are expecting to see that reflection across the line y equals x. So let's go ahead and make sure we add that in to help us visualize that. So we're going to have here's the line y equals x. Now let's graph f of x first. So we're going to have 0, negative 2. So 1, 2. Okay, there's our first point. Then we're going to have 2, 2. So 1, 2, 1, 2. We're going to have that point. Okay, so then connecting this. We have this is f of x. Now we want to graph f inverse of x. So do the same thing, plot our 2 points. We're going to have 0, 1, and we're going to have 2, 2. Oh, actually, you know what? That was not a good sketch. Okay, so, and here it is. Okay, and again, hopefully you can see this idea of reflection, because yet again, if I take this line and I fold it over, so I take this portion, right, and I fold it over the line y equals x, this is exactly what I'll get. And if I take this portion and I fold it over the line y equals x, this is exactly what I'll get. Again, this idea that both these lines are just reflections of each other across the line y equals x. Okay? So, that's it for our graphic example. Now I want to go ahead and move into our into an interesting discussion about still relating to these graph of inverses. So let's go and talk about that next. Okay, so for our next topic of discussion, I want to consider these following two claims I'm going to make. All right. The first claim is this: f of x equals x squared has no inverse. However, f of x equals x squared with the condition or the domain that x is greater than or equal to 0 has an inverse. And that inverse is the square root of x. Okay? So here are my claims. Now, are they true? Well, I'm going to say that they are. The question then is why? Why are they true? Well, let's go ahead and talk about that. But before we get into talking about that, I do want to make this important note. And that's this idea that there are functions that do not have inverses. In fact, it's probably a good, clean mix between the amount of functions that have inverses and the amount of functions that don't. Not all functions are invertible, and it's actually a pretty when you get to calculus and other higher level math classes, it actually becomes a pretty important question to ask: is the function I'm looking at invertible? And the answer to such questions kind of become quite nuanced and can kind of get real heavy in mathematical meaning and exposition about whether they have an inverse or not. Now, for us, we don't need to get that deep. What we're about to see and what this discussion we're talking about right now is going to lead us to is that there's going to be this nice, quick and easy test we can use to determine whether a function is invertible or not. But I just want to emphasize that now before we move forward is never assume that all functions are invertible. Never assume if I give you a function that an inverse exists. It may actually be the fact that the function is not invertible. A very important thing to remember whenever we're talking about inverses. Okay, so with that out of the way, let's get back to this claim I made. And I'm going to state right now that both these statements are true. F of x equals x squared does not have an inverse, but f of x equals x squared with this added condition does have an inverse, in which that inverse is the square root of x. Now, why is that the case? Well, in order to answer why that is true, we need to consider the graphs of these functions. Okay? So for the first one, the graph we generate is a parabola, right? We should all remember that. The graph of x squared is a parabola. Okay. Now then, the graph for the second function with the condition added on, right? So we just think about it. Here's the complete graph of x squared. Now, I want to do the same function, but I only want to use x's that are greater than or equal to 0. In other words, I don't want to use any negative x's. So we should be able to quickly see that means my graph is just half of the u. Okay? So here it is. Now, let's go ahead and use the connection between the graph of a function and its inverse graph. That being, it's just a reflection across the line y equals x. And let's go ahead and sketch what both those inverse graphs would have to look like. Alright, so here is f of x. Okay? So now let's do reflection. For both of these, let's do a reflection across y equals x. And let's make the sketches of what their inverse graphs would have to look like. So, go ahead and visualize for yourself. If we had the line y equals x cutting across this, okay, and we want to reflect it across, either take my word on it or see for yourself, the image we end up creating is this. Alright, that's the image I end up creating. And conversely, for over here, the graph I end up making is this. Okay? So again, how are we getting that? We are taking the line y equals x, and we are reflecting across that line. So if you reflect our parabola u across the line y equals x, you get this sideways u. If you reflect this half u across the line y equals x, you get this half sideways u like this. So here, it is only here, after we have constructed the proposed graphs of these inverse functions, that my claims, the evidence to my claims becomes clear. Because let's go ahead and look at these two functions, or these two graphs we just made. And let's recall that when we're talking about inverse functions, right? Inverse functions are still functions, right? They are everything that is true about a function must be true about must be true in regards to an inverse function as well. And with that in mind, let's take a bit closer look at these two images I drew. In particular, let's take a closer look here. There's something off. There should be something unsettling about this image for us, right? If this image is supposed to represent f inverse of x, in other words, it's supposed to represent a function, well, we should find trouble with that. And actually, I encourage you, pause the video now. Pause the video and think to yourself why this can't satisfy in being the image of a function, or the graph of a function. So go ahead and pause the video and give that a thought now. Right? So, hopefully you remembered. If not, no big deal. We're going to review it now. Hopefully you remembered the idea behind the vertical line test. Right? What did the vertical line tell us? Or the vertical line test tell us? It said that given the graph of an equation, if you are not able to draw a vertical line through the graph in which that vertical line intersects at more than one point, then you have the graph of a function. In other words, if I'm ever able to draw a vertical line through my graph and that vertical line crosses at more than one point, then the graph of that equation cannot represent a function. And if I look here, that's exactly what I'm able to do. I can draw a vertical line in which it crosses at more than one point on my graph. Hence, this graph cannot represent a function by vertical line test, right? By vertical line test, this cannot be a function. However, for this second example, right, hopefully what we can see is that no matter where I draw my vertical line, it's only ever going to cross the graph once. Oh, once. Hence, this graph is a function. All right. So going back to the one over here, and what this is going to help lead us to is this is how we're going to be testing for whether a graph is an inverse or not, is because take this image we just made and rotate it back up here. Take this image and undo your reflection, all right, and take that vertical line with you, and what you see is that vertical line ends up becoming a horizontal line once you undo the reflection. All right. So our original function f of x is a function. This original graph, the parabola, does pass the vertical line test. Nowhere can I draw a vertical line that crosses more than one point, but I can draw a horizontal line that crosses at more than one point. Okay? And that idea right there is going to lead us to something known as the horizontal line test. So let's go ahead and describe that now. Okay, so with that whole visual example we just went through was building up to this idea of the horizontal line test. And what the test says is this: a function f of x has an inverse if and only if no horizontal line intersects the graph of f of x at more than one point. All right? So in other words, your function can look however it wants to look, however crazy manner it wants to look, as long as you cannot draw a horizontal line that crosses at more than one point, you're good to go. All right? And hopefully what you're able to see from that previous visual example we just did is that this horizontal line test is a direct result from the vertical line test. Hence why they have such similar wording. All right? But unlike where the vertical line test determines if something's a function or not, the horizontal line test is used on things that are already functions, but determines if that function will have an inverse. So, just to do a quick example related to this, let's go ahead and use the horizontal line test to determine, to see if f inverse exists. All right, and we'll do it for three separate functions. We'll do it for f of x equals x cubed plus 1. F of x equals absolute value of x, and f of x equals square root of x for x greater than or equal to 0. Okay, so what I encourage you now is this should not be too difficult of an example. So go ahead and pause the video, work through this, create quick sketches, and actually for some of these, and actually for all of them, if you have a well enough understanding of parent functions at this point, you shouldn't even need to be able to create the sketches. Just through the understanding of what these graphs look like in your head, we can quickly identify whether these have inverses or not using our horizontal line test. So go ahead and pause the video now and see if you can answer this question with a simple yes, no, blah, blah, blah. All right, so go ahead and pause now. Okay, so hopefully you created the sketches or just had an understanding of the parent functions, and what you'll see is that this function has an inverse, this function does not have an inverse, and last one does have an inverse. Okay, so there it is. That's our lecture video for today. We have now introduced this idea of inverses and the graphs of inverses. Besides that, if you have any questions, feel free to email me and we can meet through Zoom or figure out something else out. And hope everyone is continuing to stay safe. Have a nice rest of your day, and I'll see you guys in the next video.